We're on the brink of a revolution in aviation. But could this new hybrid engine actually push the industry forward, or will it just leave us grounded in more problems? For years, aircraft designers have explored electric propulsion due to its promise of quieter flights, lower emissions, and reduced fuel use compared to traditional engines. However, adopting this technology hasn't been straightforward, mainly because energy storage systems like batteries are heavy and limit how far planes can fly. As the push for greener aviation grows, efforts to develop electric and hybrid electric propulsion have intensified. Since the 2000s, many electric-powered aircraft designs have emerged. NASA predicts that by 2035, commercial planes will start using electrified propulsion systems. A hybrid electric aircraft combines traditional fossil fuel engines with electric motors to power the plane. Typically, electric motors handle takeoff and landing, while fuel engines take over during cruising. The electric motors run on batteries or energy sources like fuel cells. Although HEA technology is still in its early stages, it's gaining attention for its potential to make air travel greener, much like the impact of electric vehicles. Well, charging time for HEAs depends on the aircraft's size and design. For example, Swedish manufacturer Heart Aerospace's Heart ES-30 planes, ordered by airlines like Air Canada, United, and Mesa, are expected to charge in 30 to 50 minutes. In earlier tests, engineers from the University of Cambridge experimented with a hybrid electric plane that could even recharge its batteries mid-flight, showcasing innovative possibilities for this technology. The range of a hybrid electric aircraft varies depending on factors like size, weight, energy storage capacity, and flight conditions. The Heart ES-30 can cover 125 miles purely on electric power, or 250 miles when using a turbine generator fueled by sustainable aviation fuel. Other HEA projects are also pushing boundaries. For instance, Lilium and City Airbus focus on urban mobility. Boeing Aurora eVTOL and By Aerospace Sunflyer 2 aim for regional travel. Some business and regional aircraft claim ranges of up to 621 miles with seating for around 10 passengers. The primary fuel source for HEAs depends on the design of the aircraft. Most still rely on aviation fuel, including sustainable aviation fuel, which is a more eco-friendly alternative to traditional jet fuel. But the electric motors, which power key phases of the flight, are typically fueled by batteries. These batteries can be charged using a variety of sources, everything from conventional grid electricity to renewable energy like solar or wind power. The possibilities for charging are expanding, making HEAs a promising option for reducing carbon emissions in aviation. Now, a hybrid electric aircraft consists of a few key components working together to make that magic happen. First, the traditional engines provide primary propulsion during the cruise phase of flight. The electric motors take charge during takeoff, landing, and sometimes during cruising to reduce fuel use. The electric motors are powered by an energy storage system, which could use batteries, fuel cells, or a combination of both. There are also electronics to control how electricity flows between the motors, storage systems, and traditional engines, ensuring everything runs smoothly. The control systems make sure the engines and motors work in sync, maximizing efficiency and safety. Hybrid electric aircraft are designed to reduce fuel consumption, particularly during the fuel-heavy phases like takeoff and climbing. Electric motors provide an extra boost during these stages, reducing the workload of traditional engines. When the plane reaches cruising altitude, the conventional engines can take over. As the aircraft descends and prepares to land, the electric motors kick in again, helping slow down the plane and cutting down on noise pollution. This hybrid approach can significantly reduce fuel burn, especially by minimizing the use of traditional engines during takeoff, climbing, and landing. The result? Less fuel consumption and a greener flight experience. It's clear that hybrid electric aircraft are a key player in the future of eco-friendly aviation. The technology behind hybrid electric aircraft is advancing rapidly, especially in the areas of battery development, electric motor efficiency, and alternative fuel sources. One of the most crucial breakthroughs is the development of lighter, more powerful batteries. These batteries are the key to extending the range of HEAs, allowing them to fly longer distances without the need for refueling. As battery technology improves, HEAs will become more practical and efficient, making greener flights a reality. But it's not just about batteries. Electric motors are becoming more efficient, meaning the entire propulsion system is operating at higher efficiency levels. Alternative fuels, like biofuels or hydrogen fuel cells, are also playing a significant role in reducing the environmental impact of HEAs, pushing the technology towards even greater sustainability. On top of that, power management systems are getting smarter, optimizing the use of both electric and traditional energy sources for the best performance and fuel efficiency. Materials and aircraft designs are evolving as well. New materials like carbon fiber composites help reduce the overall weight of the aircraft, boosting its efficiency. Modern aircraft designs, such as distributed electric propulsion or tilt-wing configurations, are offering new ways to enhance performance while keeping things light and efficient. But one of the most critical factors in the performance of HEAs is energy density. This refers to how much energy a battery can store for each unit of volume or mass. The higher the energy density, the more energy a battery can store in a smaller, lighter package, which directly improves the aircraft's range and performance. Simply put, batteries with higher energy density can take the aircraft farther without adding significant weight, making for a more efficient takeoff and a longer flight. As battery technology advances, higher energy density batteries will make HEAs more viable, allowing for longer flights and bigger aircraft. This makes improving energy density one of the most exciting areas of research for the future of hybrid electric aviation. While battery technology has certainly come a long way, energy density remains a limiting factor for HEAs, especially when compared to traditional jet fuel. Right now, the energy density of even the most advanced lithium-ion batteries is still much lower than that of jet fuel. To provide the same amount of energy, batteries would need to be significantly larger and heavier, which creates a challenge for the aviation industry, which requires lightweight technology for efficient flights. That's where the hybrid approach shines. HEAs combine batteries with traditional combustion engines, which help overcome this limitation. However, ongoing research into improving battery energy density is crucial. As technology continues to evolve, HEA's range and performance will continue to improve, bringing us closer to a more sustainable future for aviation. Now, the Heart ES-30 is currently one of the most ambitious electric aircraft projects, designed to carry 30 passengers. It's an upgrade from the company's previous model, the ES-19, which could only hold 19 passengers. Although the ES-30 has not yet been fully tested, the engineering team has already conducted tests on the ES-19's electric propulsion system with a ground-based prototype in 2021. For the ES-30, a full-scale test facility and flight simulator have been built, and flight testing is planned for 2026. In the meantime, other aircraft have completed test flights with smaller capacities. For instance, a modified Cessna Caravan 208B flew for 30 minutes in 2020, solely powered by electricity, with only the pilot's seat on board. Similarly, Voltero's Casio has flown in multiple configurations, including options for 4, 6, and 9 seats. For now, the focus remains on smaller, lighter aircraft, but the Heart ES-30 is pushing the boundaries of electric aviation for larger passenger loads. Now, electric aircraft rely entirely on electricity, either stored in batteries or generated through solar panels. Electric motors power propellers or turbines, and they come with clear advantages. Unlike combustion engines, electric motors don't lose power at higher altitudes, so there's no need for turbochargers. They're also quieter, cleaner, and need less maintenance. Well, not exactly. Batteries are much heavier than fuel and have limited range, which becomes critical since recharging aircraft requires ground-based resources. Another issue is heat management. Electric motors release about 20% of their energy as excess heat, which must be effectively cooled. So what's being done? To overcome these problems, researchers are working on innovative solutions. Lightweight materials and advanced designs are being developed to improve performance while reducing weight. New power and thermal management systems aim to increase efficiency and keep components cool. Despite the challenges, progress continues, driven by the vision of making aviation more sustainable. Now, hybrid electric aircraft use both electric motors and internal combustion engines, combining the strengths of each to enable longer flight ranges compared to fully electric planes. These systems can operate in two main configurations, parallel or series. In the parallel hybrid system, the electric motor and fuel-burning engine share a common shaft that powers the aircraft's fan. Either or both can provide propulsion, depending on the need. While this setup can save more energy and reduce emissions slightly better than its counterpart, the design is more complex due to the interaction of two power sources. In the series hybrid system, only the electric motors are connected to the fans. The combustion engine drives a generator, which powers the motors or charges the batteries. Series systems are simpler and support distributed propulsion, allowing multiple motors and fans to be used across the aircraft. In addition to hybrid and electric propulsion, several exciting technologies are emerging that could transform the aviation industry. One of these is solar-powered aircraft. These planes use solar panels to capture sunlight and store energy in batteries or hydrogen for when the sun isn't shining. While solar-powered planes aren't yet practical for commercial flights due to power limitations, they have already proven effective in uncrewed aerial vehicles, which can fly for months at a time, although at low speeds. These UAVs could be useful in areas like telecommunications and imagery. Another promising technology is turboelectric propulsion, where gas turbines generate electricity to power electric fans. This system could help cut down on emissions. There's also a variant called partial turboelectric propulsion, where a mix of electric motors and gas turbine provides the necessary thrust. Lastly, electric VTOL, or vertical takeoff and landing aircraft, are being developed to take off and land without needing runways. These electric-powered vehicles could revolutionize urban air mobility, providing on-demand air taxis, regional transportation, and freight delivery, opening up some new possibilities for fast and efficient travel in cities. You see, building and flying a hybrid electric aircraft comes with significant challenges, especially when it comes to designing the hybrid propulsion system for maximum efficiency and performance. But the problem doesn't stop there. Creating new aircraft designs for HEAs is a complex and expensive process that needs to meet strict safety and performance standards set by aviation authorities. Since HEAs are based on emerging technologies, there's often no clear regulatory framework in place, which makes getting them certified a longer and more difficult process. On top of that, new infrastructure, like charging stations, is needed, adding to the costs. To tackle these obstacles, engineers and researchers are working on several fronts. They're developing more efficient electric motors and improving the integration between electric and traditional propulsion systems. The goal is to create aerodynamic designs that reduce drag and increase efficiency, making the aircraft more sustainable and practical. In terms of materials, research is being done to develop stronger, more heat-resistant materials that can withstand the extreme temperatures and pressures found in aviation. Meanwhile, on the regulatory side, aviation authorities are working to create the standards, certification processes, and infrastructure needed to support the growing HEA market. Several companies are in the race to develop hybrid electric aircraft, each taking a unique approach to integrating electric propulsion systems into aviation. And Hart Aerospace is leading with its ES-30. Airbus created the E-Fan-X, a hybrid electric aircraft demonstration in partnership with Rolls-Royce and Siemens. Unfortunately, the project was cancelled during the pandemic, but still demonstrated the potential of hybrid electric technologies. Boeing is working on a hybrid electric propulsion system for aircraft. They've been modifying a test aircraft and supporting the development of a megawatt-class hybrid electric propulsion system with GE Aviation. Sikorsky Aircraft, known for its helicopters, is developing a hybrid electric VTOL aircraft. Their Sikorsky Autonomy Research Aircraft is a reconfigured version of the S-76B helicopter, showing how hybrid electric systems can be adapted to different types of aircraft. Earlier this year, ZeroAvia made strides with its Dornier 228, a testbed aircraft where one turboprop engine was replaced by a hydrogen-electric powertrain, featuring fuel cells and a lithium-ion battery. This marks a significant step towards cleaner, more sustainable aviation. Well, they're optimistic about the future of hybrid and electric aircraft, particularly in smaller settings. Industry leaders believe that HEAs will be first used in short, urban commuter routes, paving the way for larger, scalable technologies. Györgyn Çınar, a professor and aerospace engineer, sees hybrid propulsion systems as a promising option, especially for regional aircraft in the 2030 to 2035 timeframe. She notes that using batteries during takeoff and climb could significantly reduce fuel burn, with hybrid systems providing a mid-term solution for larger jets. The widespread use of HEAs could have a profound impact on the aviation industry. Environmental benefits stand out as one of the biggest advantages. HEAs could drastically reduce emissions, helping fight climate change and air pollution, both growing global concerns. For airlines, HEAs could reduce fuel consumption and maintain costs, making air travel more affordable and accessible. These improvements could lead to faster, more reliable flights with fewer delays. The addition of VTOL technology and short-range, affordable travel could open up new routes and destinations, especially in underserved areas. HEAs are also quieter than traditional aircraft, reducing noise pollution around airports, particularly during takeoff and landing. But developing large passenger HEAs requires overcoming significant technological and regulatory challenges. However, companies like Ride Electric are aiming high. They're working on a 186-seat commercial jet with an 800-mile range, expected to launch by 2030. Additionally, their Wright Spirit, a 100-seat electric aircraft, could take off by 2026, marking a huge step in the future of hybrid electric aviation. Now, what do you think about the future of hybrid electric aircraft? Do you see them replacing traditional planes soon? Don't forget to like, subscribe, and comment below with your thoughts. And if you're curious about the future of aviation, click here to watch our next video on this new Rolls-Royce engine that's coming soon and that will revolutionize the entire aviation industry.